Do something for me. Open up your browser and type quantum computer. What do you see? Do you see gold? Does it look like a chandelier? If so, you're in the right spot. Every once in a while, these photos go viral. First it was IBM, then it was Google, and then it was Microsoft. But the thing that you searched up isn't a quantum computer. Then what is it? It's a dilution refrigerator, but not the kind that preserves your food. This fridge can go as low as 10 millikelvin, 0.01 degrees above absolute zero, colder than space. So let's dive in. Okay, this might look a little bit intimidating, but trust me, it isn't. You have to think about it like this. You can't get from 300 Kelvin to 10 millikelvin in one cooling step, which is why you need all of these panels to get down step by step. The first step of cooling is the flange, which is over here. How else are you going to separate what happens inside the refrigerator from the outside world? The flange acts as a vacuum seal, which means that whatever is happening inside of this is a vacuum. That's how temperatures get so cold inside the refrigerator. The second stage over here is the 50 Kelvin radiation shield. This shield is what separates the helium from here to the helium from here. This acts as a shield to block out all of the radiation. The 4 Kelvin radiation shield is next. This also happens to be the point where gaseous helium turns into liquid helium. This acts as a second radiation shield, blocking out even more radiation. So it's about similar to the 50 Kelvin radiation shield. Now this is where it starts to get really cold. Between these two plates, where all these lines are, is known as the still. When you get so low to 0.7 Kelvin, this is where two different isotopes of helium start splitting, helium-3 and helium-4. Think about isotopes as different versions. They have different amounts of neutrons. Helium-3 has 2 protons and 1 neutron, and helium-4 has 2 neutrons and 2 protons. Helium-4 is the more standard version, so as a result, since helium-3 is much more volatile, it starts getting whiffed away, pumped away. That is the still's job, and it makes the entire thing cooler. Next up, we have the cold plate. The cold plate over here is the final heat exchange between 0.7 Kelvin and 0.1 Kelvin. This is the point where it starts to get really cold. This tiny machine here underneath the cold plate is what's known as the mixing chamber. I will explain this to you later, but here is where helium-3 and helium-4 start mixing with each other, causing endothermic reactions. This makes the entire mass of helium way cooler. And so finally, we have it. This is where the quantum computer is located. These are the wires that go all the way up here, see this, all the way down here. These basically transmit signals. This tiny box right here is just the box where the quantum computer is held. The actual quantum chip is very tiny. Of course, there's a plate here, and then you can see our quantum computer is that little black dot. The thing that stands out to most people is the gold. Why gold? Isn't copper so much better at conducting electricity? Well, gold is just the plating. The actual thing is, of course, made out of copper. That is how you get the superconducting quantum computer. However, gold is used on the outside for its very low emissivity. This emissivity is a scale from 0 to 1, where 0 means that it emits 0 infrared radiation, and it holds everything in. 1 is, of course, the complete opposite. Gold is the closest to 0 that we can get, so naturally we need gold plating to trap in or trap out the heat. Earlier, I was talking about the chip's location, but temperature is the only one thing that the chip needs to be kept away from. It also has to be cold, dark, magnetically silent, and mechanically still. All of these things could create vibrations which would affect the fragility of the quantum computer. Think about it like this. This entire refrigerator is used just for this small quantum computer over here. That is mind-blowing. The first reason why quantum computers need to be so cold is because of superconductivity. Quantum computers are superconducting computers, which means that they rely on zero electrical resistance. Heat has electrical resistance. The second reason why quantum computers need to be so cold is because of their fragility. Quantum information, or qubits, are locked in superposition, meaning unlike a normal bit, which is either 0 or 1, quantum bits are technically 0 and 1 at the same exact time. This means that quantum computers are not only more efficient, but their information is so much more fragile. Just a little bit of vibration from heat could collapse the information, defeating the purpose of the entire quantum computer. Alright, so the journey of our helium atoms start outside of the dilution refrigerator. It's just pretty simple. The helium atoms are moving freely at 300 Kelvin, which is just room temperature, outside of the flange, and you can see the wiring, of course. Next, we go past the 50 Kelvin radiation shield. Now, you might be asking, what is a pulse tube? A pulse tube cryocooler is a conventional method of cooling things down to extremely low temperatures. This one goes down to 50 Kelvin. Basically, what you should know is that it moves the helium back and forth between the tube that we're seeing here, and that is how it's cooling things down. Pretty complicated, so I won't go into much detail in this video. Next up, we go past the 4 Kelvin radiation shield. Now, you see a condenser here and a reservoir here. You also see a cold head. What you should know is that the condenser is going through the rings of the cold head. This condenser is condensing down the helium into the reservoir, which turns gaseous helium into liquid helium. Now we have it at 0.7 Kelvin. At this stage, helium-3 and helium-4 isotopes start to split away. Helium-3 is a lot more volatile, so in this low-pressure environment like the still, the helium-3 preferentially goes away, and it cools the rest of the mixture. It's like how sweat cools your body. Now, finally, we get to the mixing chamber. This is 10 millikelvin. As you can see, on the top, we have the less dense section of helium-3. Not pure helium-3, but it's definitely mostly helium-3. Now, since it's on the top, it would obviously have an incentive to go to the bottom, to the helium-4 section. This is where the dilution in dilution refrigerator comes from. This helium-4 section is a lot more dense, while the helium-3 section is a lot more dilute. There's a very specific amount of helium-3 that can dissolve in helium-4. It's the helium-4 solubility, like how water can only hold a small amount of sugar before it obviously can't dissolve anymore. That number is about 7%, so the mixture can be about 7% helium-3, and then it has to be pumped out. But wait, if you were paying attention, I skipped a step between 0.7 Kelvin and 10 millikelvin. But what is this heat exchanger supposed to mean? I mean, what even is this? Why is helium-3 going up and down? Where even are we? Currently, we're in between the still and the mixing chamber. The top is the still and the bottom is the mixing chamber. And that is where our pump is leading away the helium-3 atoms. It's not just leaving the entire system, it's going inside the heat exchanger to go down to the mixing chamber. So let's look at this through the eyes of a helium-3 atom. Our journey starts in the still. Helium-3 is much more volatile, so, like I told you before, it gets pumped away. After a helium-3 atom gets pumped away, it goes inside the heat exchanger, where our helium-3 atom is one of the orange atoms that are going down from the left of the heat exchanger. In the heat exchanger, we meet cooler atoms which just came out of the mixing chamber on the right. These are going up to the still. Since we have a bunch of heat, we naturally transfer the heat to our partners on the other side of the heat exchanger. Finally, we're back in the mixing chamber. Think of one of our helium-3 atoms as the one that's crossing over just now. This atom wants to go dissolve in the helium-4 section. It wants to. Now, moving over from the helium-3 to the helium-4 section costs energy. Now, this energy is borrowed from the quantum computer. The quantum computer obviously has energy and wants to give it away because the quantum computer needs to be as cool as possible. And the helium-3 atom uses it, and it goes back up into the still. If you enjoyed this video, then please consider subscribing. I have plans in the future to post bi-weekly videos about quantum mechanics. Again, it's free, it takes 5 seconds, and it helps me out a lot. So thank you, and I'll see you next time.